Hello, everyone. My name is Hugh Lee from UC Irvine, and welcome to my talk on CV Inspector towards automating detection of adblock circumvention. This is joint work with Athena Markopoulou and our collaborator Zubair Shafiq. Given a general scenario of no adblocker, when a user visits a site, the site would retrieve ads from an external server and place it onto the page. Now, if the user installs an ad blocker, the ad blocker may stop the retrieval of ads by blocking web requests or even hide ads that are already on the page. Now, with adblock circumvention, the page detects that an ad is missing. It would then utilize specialized techniques to circumvent the ad blocker to retrieve a new ad and re-inject it back onto the page. Now, these new ads may have different HTML structures to prevent ad blockers from hiding them. The key players within this arms race is as follows. On one side, we have publishers and advertisers that want to display ads to earn revenue, and as a result, they may employ circumvention techniques. CV providers are also a key player. They are third-party services that can integrate directly with publishers to help employ circumvention. On the other side are ad blockers, who utilize filter rules to block ads and tracking. Now, filter rules are basically patterns that can match with web requests to block them, or match with DOM elements on the page to hide ad elements. And these filter rules are maintained by filterless authors. To combat circumvention, ad blockers utilize advanced filter rules, and we call this anti-circumvention. Our work systematically studies both sides of this arms race. For anti-circumvention, we focus particularly on Adblock Plus due to its popularity and because of its concentrated effort for anti-circumvention. For example, in 2018, they created a new team just to monitor circumvention on the web, and we were able to collaborate with some of the members of this team as well. With this effort came a new filter list called the anti-circumvention list. This list supports advanced filter rules, such as being able to block the execution of JavaScript. Now, filter lists are commonly available to the public in the form of GitHub repositories. So to understand how much effort filter list authors put into maintaining the effectiveness of the filter rules, we look at its GitHub repository. First, we look at the time between commits for the anti-CV list. Here we discover that the most common time is 4 minutes. When we compare this to the most popular filter list called EasyList, the anti-CV list is on average 8.7 times faster. Next, we look at the coverage of the web that the anti-CV list has. Here we extract sites from the filter rules and then match them with the Tronco ranking. We find that around 927 sites are within the top 1 million. And also the plot shows that there's a widespread coverage of the web, even beyond 1 million. This highlights how much effort is needed to maintain the filter lists. Our work, CV Inspector, aims to reduce the effort for filter list authors. At a high level, CV Inspector works in the following ways. Given a list of sites, we feed it into CV Inspector. It would then output whether a site is CV. This means the site was able to circumvent the ad blocker, or no CV. This means the site did not attempt at circumvention, or it was unsuccessful at circumventing the ad blocker. We envision CV Inspector to be integrated into the workflow of a filter list author. For example, once again, given a list of sites to CV Inspector, the filter list author will only need to be focused on sites that were able to circumvent the ad blocker and then update the rules for them while ignoring all the other sites. The rest of our presentation is as follows. We'll give details on how circumvention works. We'll introduce the design and evaluation of CV Inspector, and we'll conclude with a summary. Circumvention can be categorized into either cloaking or obfuscation-based techniques. Now, prior work has studied cloaking-based techniques extensively, and in the interest of time, we will refer to the paper for details. Our work focuses on obfuscation-based circumvention, since they are longer-lasting techniques that have caused ad blockers to put in high human effort to combat it, as we saw earlier. A general workflow of obfuscation-based circumvention is that the site can detect an ad is missing, It will then send an obfuscated ad request to a circumvention server. This server will be able to handle that request to retrieve real ad content from ad servers and then obfuscate that ad content before sending it back to the browser. Now, JavaScript will then rebuild the ad content and then re-inject it back onto the page. Specifically, for circumvention, they can randomize URL components. This corresponds to steps 2 and 4. Now, this makes it difficult for filter rules to target web requests to block. Another technique is to alter the DOM structures of ad elements. This corresponds to steps 5 and after step 6. This makes it difficult for filter rules to target ad elements on the page to hide them. A third technique is for publishers to integrate directly with CV providers so that they can display third-party ads as first-party ads. Now, this makes it difficult for ad blockers in general because commonly they focus on only third-party ads. As we can see, these techniques are designed to make it difficult for filter rules to target. This motivates our work on CV Inspector to help detect when the site can circumvent the ad blocker automatically. Next, we'll talk about the design and evaluation of CV Inspector. The inner workings of CV Inspector is as follows. Given a site to CV Inspector, it will then visit the site in two main cases, A, no ad blocker, and B, with an ad blocker. Here, note that we utilize EasyList for AdBlock Plus. It would then collect data such as web requests, DOM mutation, temporal events, which are just timestamps, and the page source, which is HTML, inline CSS, and inline JavaScript. We do this 4 times per page to capture the dynamic nature of the site. We then aggregate all that data and employ differential analysis. This allows us to identify unique events that only happen when an ad blocker is present. We then do feature extraction and feed it through our random forest classifier. And once again, the output is CV or no CV. For feature extraction, we rely on what we learned about obfuscation-based circumvention. We will summarize a few top features. Now recall, a technique is to randomize URL components. Here, when we compare examples of a normal URL with an obfuscated URL, we can clearly see that the path is highly randomized. To capture this, we calculate the entropy of strings for the path. And this turns out to be a top feature. Next, recall that we can alter the DOM structure for ad elements. As a result, this causes changes on the page. To capture those changes, we utilize DOM mutation observers. And we find that a top feature is the number of DOM nodes being removed. Now, this actually showed that sites are cleaning up some of the node elements before reinjecting ads onto the page again. Next, recall that new ads are being reinjected onto the page into certain ad locations. To infer whether the reinjection was successful, we rely on our page source data. For example, given a page source for no ad blocker, we identify the locations of third-party iframes. We then dynamically build CSS selectors for those locations and then apply the selectors to the page source of with ad blocker. We then count the number of iframes and images that are still visible to the user within those locations. And in fact, this becomes a top feature. Overall, CV Inspector utilizes 93 different features. Next, we'll discuss our ground truth methodology. As there are no good data sets currently available, we must make our own ground truth. First, we extract sites from the anti-CV list, as these sites implicitly attempt circumvention. We also consider the Tranco Top 2K to make sure our ground truth covers the most popular sites. We then have a team of 2 undergraduate students who helped label our data sets. However, there is a challenge as finding positive samples is not trivial. Now recall that in order for a site to be a positive sample, it must be able to successfully circumvent the ad blocker and not just attempt at doing so. And as a result, our labelers would need to inspect thousands and thousands of sites. So we devised a methodology to identify CV sites, which are positive samples, to reduce the labeling effort. We iteratively train our classifier and then use it to prioritize which sites to label first. For example, we first label 500 sites and add it to our ground truth. We then train our random forest classifier. We apply it on the remaining unlabeled data, and then order it by decreasing classifier confidence, and then choose the top 500. So these sites are the most probable sites of being a positive sample. We then verify that by labeling those top 500, and then continue with a new iteration. Now, with this, we can actually stop this whole process once the classifier's performance plateaus. For example, when we plot the number of iterations with the corresponding F1 score, we find that it only took 3 iterations until the classifier performance plateaus. This means we do not need to label all the sites within these sources. This makes the life of our human labelers much easier. So now we have our ground truth, and the result is we have around 1,566 sites of no CV. We call these negative samples. And then 755 sites with CV. We call these positive samples. We evaluate CV Inspector in the following ways. To understand how it performs on the ground truth, we do a 5-fold cross-validation. Here, CV Inspector achieves 89% when identifying sites that can circumvent an ad blocker, and 94% when it cannot. We also apply CV Inspector on a data set that was generously provided by AdBlock. These sites are known to be aggressive on employing circumvention, and thus filterless authors must continuously monitor them to update filter rules. Here, CV Inspector achieves similar results. We report precision here because when we validated this result, we sampled the data instead of labeling everything. Next, to understand how CV Inspector works on the top sites, we apply it to the Trunco top 20K. Here, once again, CV Inspector achieves similar results. In conclusion, we showed that anti-circumvention involves high human effort to maintain the effectiveness of filter rules. And so CV Inspector can help to reduce that human effort by being able to automatically detect which sites were able to circumvent the ad blocker so that filterless authors can only focus on those sites to update the rules for them. We have open source CV Inspector, including an Amazon machine image for quick use and a ground truth dataset. Special thanks to our undergraduates, Yiyu and Yang, for helping us label the sites. And also thank you to the team at Adblock and IO for providing insights into circumvention and also providing a dataset to evaluate CV Inspector. Thank you.